Right, thank you. So, as David said, I'm Bill Langdon at Press Centre. What I wanted to talk to you about was some work that's coming up in the genetic improvement special issue of Genetic Programming and Evolvable Machines. There's an article there, it's already online, but it will be in the next issue of the journal, where we classified work on genetic improvement and running on graphics cards into basically four classes. The one, so those are labelled out here, the one I'm going to concentrate on today is Barracuda. So the talk today is going to be about Barracuda. The first question was why would you be interested in running stuff on graphics cards? And fundamentally the answer is speed. The green line is over time performance, at least this is peak performance of NVIDIA graphics cards against peak performance on CPUs, single and double precision. And you can see that the NVIDIA graphics cards have come out on top consistently, and the gap is getting bigger and bigger. So in terms of why you might be interested, it's simply a question of speed. In terms of programming graphics cards, the easy answer is don't. Programming graphics cards is hard. If you can, the way to go is always to use high-level languages, high-level libraries, but those are usually only good for doing matrix operations or simple vision operations. If you want to do something that's general purpose, and you want to get advantage of the performance of the hardware, you end up falling down into something like CUDA, OpenCL, which is C-like languages. They're difficult to program, they're hard to get right. Once you've got the code that's correct, it's hard to get performance. And so what we've been looking at is there scope for evolving existing CUDA code to make it in some ways better? And typically better means faster. And so what I'm going to do is concentrate on Barracuda. So what I've got is about 10 minutes of material. So I'm expecting you guys to contribute about 20 minutes to my talk. First question, what is Barracuda? Barracuda is a DNA analysis tool. It was written about 6 years ago. It's about 8,000 lines of C code, which was ported from this tool, BWA, which is a traditional Unix utility, ported by experts in CUDA, by experts in bioinformatics, to run on CUDA code as it was 6-7 years ago. The way it's its speed is essentially what you take is a sequence of DNA strings. For each one, the goal of Barracuda is to spew out where that DNA lies in the human genome. So for each of these, you should get a location. It gets its speed by doing about 160,000 of these in parallel. So you're expecting your graphics card to run 160,000 threads. And naturally that runs much faster than doing them one at a time. This is not a pure AI approach. This is very much a working with the GI approach. So here on the left-hand side, we have the original host code, and this is the GPU code. In blue, I hope you can see that, is stuff that I've done by hand. So the major choice was, instead of passing all the DNA strings into this guy and running it on the graphics card, this kernel, the split inexact match caller, does a whole bunch of very sophisticated backtracking, which runs really poorly on the graphics card. This one doesn't do any backtracking and is consequently much faster. In a typical DNA scan about 85% of the data you can find an exact unique match for. This guy will do it very fast. This manually inserted piece of code says, run this, only when it doesn't produce a unique match do you fall back to the original code. So the original code is much slower. We've got most of our cases running on the faster code. So that's the manual part in blue. The red part is the stuff that was optimized by the genetic programming. So the GP optimizes not only the new kernel, but also the common code which is shared by both kernels. This making sense? Some nods, okay. Pushing on. So, as I warned you, a lot of this is, I'm going to skip past the technical details, and if you want technical details, shout at me. So, what we've done is split the GP part into two things. One, which is these 15 options. So, at the beginning of the chromosome, there's some fixed representation that says, choose these 15 options. It's just more or less like a bit string. And then we have patches, which is more like the traditional GI. We run a population which consists of 1,000 mutants. We compile those, we run them, and for each of them, we check each of the 160,000 answers it's produced. Are they correct or not? If they're correct, how fast was it? And I'm going to skip past that one, and that. So, this is schematic. We're taking the original CUDA code, and we generate automatically a grammar. It's a grammar that says what are the legal modifications of the code. So it's not a generic, like a C grammar. It's a grammar that's specific to Barracuda. We run around our evolutionary loop. In the population, we have 1,000 individuals. The rectangular part here is supposed to represent the fixed part of the representation, and then a variable list of patches. We have mutation operations, we have crossover operations, we generate new guys. From those new kernels, we attempt to compile them. So we put them all into one big source file, we attempt to compile it, and then we run sequentially our 1,000 mutants. And for each one, we say, does it produce the right answer, or at least does it produce the same answer as before, and how long does it take? So,
are you running these on the GPU?
The mutant kernels are compiled on the host in the usual fashion, and the code is shipped to the GPU and run on the GPU.
Right. Don't GPUs crash quite often? So
you
have problems with that?
The ones I've run in the last 2 years have not crashed. When I did originally start, it was very convenient to have the GPU under my desk, so I could flip the power switch about every 2 minutes. Seriously, these suckers have not had that problem. Running in an air-conditioned machine room, they're remote. If they lock up, it's a real pig. And that hasn't happened. Yeah?
Are you running these multiple times to get any sort of statistical confidence that it's actually different, or are you accounting for relatively small perturbations?
Okay, so one of the nice things about GPUs is they are extremely stable. If you take a kernel, you run it on the same data, it will take almost exactly the same time you run it again on the same data. Almost exactly meaning maybe a couple of hundred parts in a million. So the execution times are very stable indeed. What is being run on here is training data from the 1,000 Genome Project. So that's been chosen as being typical of the sort of data that Barracuda normally runs on. And again, to come to your question about variance, no. This is being run on a system which is stochastic in the first place. There's a fair amount of noise. I have deliberately not, in these experiments, tried to minimize that noise. There are 1,000 of these guys. I only want one that works. Michelle.
Yes. The question is about the grammar. What is the size of the grammar, and does this grammar prevent from finding, say, not compilable things?
Okay.
Or perhaps you...
I buried somewhere I have an answer to your question. From memory, this is not a huge grammar. I think it's probably under 1,000 rules. We have run with much bigger ones, but it's something like that. I'm sorry, I've forgotten your second question.
Does this grammar ensure that your, say, your offspring will be viable? In terms of compiler, in terms of, I don't know.
Okay, so the question was about the grammar. What the grammar ensures is everybody will be a syntactically correct CUDA kernel. Syntactically correct doesn't guarantee that it will compile. In these experiments, almost all of them do compile. By almost all, I mean probably about 99.3%. But that means that you have to have your GP system resilient against the remaining 0.7% that fail. So if something fails to compile, it can't take out the whole GP system. What happens is you give that guy 0 fitness, he never has children, but your GP system carries on running. In this experiment, the loops, and there are loops in these kernels, were deliberately butchered so that they will terminate. There's no way a kernel can run forever. If you get a kernel that runs forever, you physically have to toggle the power switch. It's really bad news. So there's a loop counter in there that says, hey, we've got really silly values, it's time to kill this boy. So the grammar doesn't guarantee that the programs will be correct, but there's a high chance that they will compile, and if they compile, there's a guarantee that they will terminate. And most of them not only terminate, but actually produce reasonable sort of answers that you can assign a fitness to. Anybody else? No? As I say, we swear out this loop 50 times, and then we spit out an answer. I'm going to skip past some of this stuff because you're supposed to be working, not me. So this, in summary, we have a fixed part, which is like a traditional GA, bit string GA, and then a variable part, which is a list of patches. The mutation, which essentially is bit flip on the GA part, or add another patch to the end of our list of patches on the variable length part, and crossover, again, a GA crossover operator on the fixed part, and something that looks like a GP crossover on the variable part. We run this on a number of GPUs. This is the tidied up version on the Tesla K20. So K20 is one of the top end, well, used to be top end GPUs. And what I've done is at the top, I've put the changes to the fixed part of the representation, and then this is the variable part. In the fixed part, the first one here is a flag which says, instead of putting the cache, the BWT cache, in local memory, put it into registers. So that, whoops. So that's what this does. We double the number of threads used to load the BWT cache, and we double the number of threads in the block. So those are fixed things that we can switch in and off, and those are the values evolution has chosen. And then these are the variable ones. So line 635, which is a for loop, we've inserted the pragma unroll. So essentially that tells the compiler, please could you unroll the following loop. Line 578 is an if condition which is never true. Evolution has spotted that it's never true and effectively deleted the if, which makes life easier for the compiler. It doesn't have to generate any code for this. It doesn't have to dedicate any registers to the code. This is similarly semantically preserving, but I'm not going to try to explain it. The last one's interesting. Line 126, we've deleted a line 126, which means effectively we've disabled a software cache. So the original code was written by hand. Somebody thought it was a really great idea to cache the last 8 values. And what evolution has decided is, I'm not going to do that. Deleting that line disables the cache, doesn't change the answers that are produced, but instead of 7 times out of 8 reading a value from cache, every time we actually have to read the value from main memory. Paradoxically, that change makes the code 3% faster. Evolution doesn't care, it just does what was told. Give me a fast kernel. So what we've done is we trained on data. We've taken another 10 data sets from the 1000 Genome Project. They've randomly chosen. So this is nothing to do with the training data. This is test data. On the K20, we get almost 2 million DNA strings a second. On the K40, we get slightly more than 2 million DNA strings per second through the kernel. In both cases, the answers are 100% identical. And this code was manually inserted into SourceForge. It's been available for almost 2 years. So when you download Barracuda, you get the GI version of Barracuda. And to conclude, on the code that we sped up, we got more than 100-fold increase in performance. When you come down to it, the whole application consists of far more than just this kernel. So in general, on real data, we're getting a speed up between 2 and 3. Depends on exactly what sort of data you're looking at and how noisy that data is. But on real data, we're getting sizable speed up. Barracuda has been incorporated. So Lab 7 is a company in Austin, in Texas. They have a product called BioBuilds, and since November 2 years ago, they've been shipping the GI version of Barracuda. Whilst I was at the last one, Gecko, we got an email from IBM that had been routed via NVIDIA. NVIDIA and IBM had got a huge contract from the Department of Energy, $325 million, to spend on a supercomputer based on NVIDIA cards and the IBM Power 80. And what they wanted to do was say, can we run Barracuda on it? And as a result, they took Barracuda from SourceForge and ported it to the Power 80. So that was about 18 months ago. More recently, there's a firm in Cambridge who are interested in using epigenetic data. So this is slightly different from DNA data, but essentially very similar. And what we've been looking at is some benchmarking to compare the performance of Barracuda on their data. So on a GTX 1080, which is top-end gaming card, Barracuda is 21 times faster on their data, on their epigenetics data, than BWA Meth, which is effectively the state of the art. And similarly, on the epigenetics data, Microsoft have been running Barracuda benchmarks on the GPU version of their Azure cloud. And that's me done, really. Thank you very much.